Yeah, thanks a lot. So yeah, so indeed I will continue this lecture, and first let me remind you a bit where we were. So first we introduced why superconducting circuits are a good platform to explore quantum trajectories and quantum control and feedback, and then we were in this second part, which is about the description, the modeling of the measurement apparatus that are used for detecting the signal coming out of these quantum systems. And so today my plan is to cover the end of this part, and then on the third one I will show experimental results that go very well in the line of what Keter has shown this morning, and Huard as well. So I hope to get there in time for today. Otherwise, we'll have the last lecture on Friday. Okay, so last time we started by introducing carefully what is a propagating mode, and so we had introduced this concept of the voltage operator, which is decomposed in two parts. So one part which is propagating towards the right of the line, and the other one which is propagating towards the left of the line. And so the speed, the velocity of propagation is the same for both. And then taking the Fourier transform and renormalizing this by a prefactor, which is sadly in a difficult prefactor in 1 over the square root of absolute value of omega, we can define these propagating amplitudes A and right and left of omega, which are the Hermitian conjugate of themselves at minus the frequency omega. So the conjugate, the commutation relations between the two is almost a Dirac function, but there is this bothering sign in front. And we can do a Fourier transform again. This time I chose to start from 0 to go back in the temporal domain, hence defining these propagating modes in the temporal domains. And so if we take the limited bandwidth assumption, limited bandwidth means that the signal is supported on a region of the spectrum which is far away from 0. Then we can easily relate the voltage operator, left or right, to the quadrature, one quadrature of this propagating mode A of tau. Okay, so then I define a discrete version of this. So in a sense, this definition with A of omega or A of tau is somewhat pathological, because it's you see that A of omega describes modes that have infinite precision in frequency and infinite uncertainty in time, and reciprocally A of tau describes modes that have infinite precision in time and zero certainty in frequency. So if we're interested in realistic modes, it's important to do something maybe a bit different. And so what I introduced here is a mode AF, big AF, capital AF, which is the weighted version of this propagating modes A left or right, weighted by a function which is in L2 of RC. So its modulus squared can be summed up. And we decide that it's normalized to 1. So with this definition, we have a much more peaceful commutation relation. So AF commutator AG dagger, where G is another function in L2 over C, and again which is normalized, is equal to the scalar product of FG. And if you take any two annihilation operators, their commutator is 0. Okay, and we define that. We can also experimentally, so this has been done, for instance, in the first, I think, in the group of Andreas Wallraff for superconducting circuits. We can engineer a single photon in any mode which is regular, let's say smooth enough, by the expression of a single photon in that mode, the mode of the wave function f. Is AF dagger applied on the vacuum. So let me continue this exploration and maybe tell you a kind of a recipe to determine what are the good modes for a given state, a given problem. So if you have a state in the line, something you can do is define the G1 correlation function. So the G1 correlation function is the average value of the creation operator at time t1 times the annihilation operator at time t2. And so if we define this correlation function, and we can diagonalize this one, so we diagonalize it with some sum of on all the possible modes k, nk times fk star of t1, fk of t2. So this is called a Carouin-Loève expansion. So interestingly, if we order the weights nk, so we can choose nk plus 1 smaller than nk. Then what we have done here is identify what is the natural basis of modes for a given quantum state. And so you can like this define if you want what are the optimal discretization of the line for a given problem. Okay. So now I'd like to go to part 2.2 and discuss the first measurement apparatus, which was the one actually that Keter mentioned earlier. So the homodyne detector. Yes. The X you said, sorry. Yes, to this. So these the FKs are an orthonormal basis of L2 of RC. And so what? So in many physical practical problems, the number of modes will be very small. So NKs. So if it's single mode, this Carouin-Loève decomposition will tell you that there's a single mode that's occupied and all the others are empty. And in some instances, it's a bit more complex. So there might be a few modes occupied. And in very complex instances, many modes are occupied. Yes. Okay. So let's discuss homodyne detection. So Huard this morning represented a homodyne detector in quantum optics. So in quantum optics, this homodyne detector is done by a beam splitter. So let's say you want to detect an incoming mode A of t. I will remove the arrow for simplicity, but this is really an incoming mode A of t here. So what can be done is send a laser beam, which because I'm doing microwave experiments, I represent like this, but this is a laser, and so it will impinge on this. You see on this beam splitter. And then what you do in quantum optics is that you send this to photodetectors. As I told you in quantum optics at room temperature, the quantum, the energy of a photon in quantum optics is very large, five orders of magnitude larger than in the microwave domain, and it's also larger than the typical gaps of semiconductors. So building photodetectors for the optical domain is something that's been done for quite some time, and there are very good detectors now. So this is a natural way to detect light in quantum optics. It's very different in the microwave domain, where I'll show you that there's advanced research right now building photodetectors. So you have two photodetectors like this, and then what you need to do is take the difference between the two intensities coming out of these detectors. And this is the outcome of what's called the homodyne detection. You can play with the phase. So here there will be it's a measurement frequency. You can play with the phase as well of the laser, and hence choose the phase of the homodyne detection. In the parallel in superconducting circuits, so in the microwave domain in general, so it's a bit different, right? So there will be a microwave cable that impinges on what's called a mixer, a frequency mixer. So again, it will be A of t. The mixer will be connected to this time it's an actual microwave generator. Same thing, right? Omega m and phase phi. And then at the output, there will be an analog to digital converter, or if you want a voltmeter, that would measure would measure the voltage as a function of time. Okay. So how does that? How can we model this more rigorously? So both can be modeled a bit in the same way. So ideally, an ideal homodyne detector, what it does is a measure a function x phi of tau, which is related to the annihilation mode of the annihilation operators of the propagating mode in such a way that it's exponential I omega mt minus phi a of tau plus hermetic conjugate. So you see it does, so it measures an observable, so it does measure here a Hermitian operator. So that's why we add the hermetic conjugate. And as you can see, it shifts. So this laser or this generator basically shifts the frequencies by omega m. Or if you prefer, we shift the frequency of the signal back to close to zero by shifting it by omega m. And again, there is this phase which we can choose, which we can tune as well, which is really important in homodyne detection. Okay. So in reality, these two experiments, they are not infinitely precise in time. So when you get 1 point on your computer, so the computer will, if you want to record the voltage as a function of time, but what it really does is give you a value in volts at each time step. But these are steps, right? There's at least the discretization of the ADC. But there might be filtering of the line before here that even smoothes a bit more than the filtering function of the ADC itself. So what I'm saying is that instead of this perfectly sharp in time operator, what we actually measure. So actually, what we measure is one of these operators for a mode defined by f, which would be so again the weighted version of this x phi of tau, d tau, with f naught. So here f of tau would be f naught of tau exponential minus I omega m tau. Okay, so you see we shift the frequencies by omega m, which we choose. And in homodyne detection, the game will be to choose omega m to be at the center of the signal of the support in the frequency spectrum of the signal. So omega m will be essentially the signal frequency, right? We will match the signal frequency to the detection efficiency. So we can define again a mode big capital AF. So we have here, you see the exponential minus I phi AF plus hermetic conjugate, yes, and so this F naught here in this since we've deported all the complex part in this rotating term. F naught is a real function, so this belongs to L2 of R in R. Okay. Okay, so what is how do we predict the probabilities to get a given measurement outcome? So let's consider one simple case first. So if the line is in the vacuum state. Okay, vacuum state in the line, so we do nothing. The line is at rest with a zero temperature bath, and so what's going to happen is that any two modes. So let's say if I want to see the correlations between a mode defined by x phi f and another mode x phi prime, let's say g. Where f and g is the scalar product on f and g is 0, so these two modes do not overlap. Then we also assume that that f and g are normalized to 1. So then there is no, so the measurement outcome of these two operators, they have no correlations. So no correlations between their measurement outcome. Okay. And the measurement outcome, so the probability when you're in vacuum of finding a given value little x for these operators is a Gaussian function. It's a Gaussian function centered on 0 if it's vacuum, and the variance is set by the vacuum fluctuations. And so if you do the math carefully with the prefactors, you should get this term in front of the x squared in the exponent. So this variance. Okay. So this is for one of these of the discretized modes. Okay, which are relevant again because the ADCs provide you voltages in time steps. But if you want to model instead something which is less physical but which would be directly this infinitely precise in time operator x phi of tau. So x phi of tau itself, well, the measurement outcome x phi of tau, you can model it with a Wiener process. So this would be the derivative of a Wiener process in time. So this is a Wiener process. So the same kind of process that Pierre discussed this morning. And this is a white noise. So the two descriptions are okay to do calculations. Of course, the continuous version might be more convenient because we can write stochastic master equations directly. But the first one is maybe more physical, easier to interpret physically, I would say. Okay. So let's do another example and see what kind of mode we may choose to characterize the measurement of a quantum system. So let's say we now have a cavity, so microwave cavity or optics actually is the same. So we have a cavity which is occupied by the quantum state psi, and this cavity is connected to a transmission line with a rate kappa. So kappa defines the infinitesimal probability that a photon escapes into the line dp if there is a single photon in the cavity would be kappa dt. That's what I mean by this rate kappa. So we do this experiment. So we connect the cavity to a transmission line, and then we connect it to our homodyne detector. So that's the ADC after a mixer and a microwave generator at omega m. So as I mentioned, the case of the case of homodyne detection is the case where we choose this signal generator frequency omega m to be equal to the resonator to the cavity frequency. Okay, we choose it to be the same. And so what's the best mode? What's the mode that would arrive in this Carwan-Noëv decomposition? What we will find is that the mode into which this cavity will relax is an exponentially decaying function of time. So it will be exponential minus kappa over 2 times tau. And so if we choose this particular weight for the demodulation, so if we define the mode x phi f with a weight which is exponentially decreasing in time with the same characteristic time scale as the coupling of the cavity to the line, then we will end up in a quantum state which so essentially the quantum state in the line once the cavity has been fully emptied, so after a time plus infinity. So the quantum state in the line would be precisely this creation operator AF dagger of the vacuum. So if we match the phase, so here I pick the phase phi equals 0 this discussion. And so if you now want to predict what's the probability to find a given measurement outcome of this detector, so we will compute the probability to find a given value x phi. Yeah, maybe I should. I will not do phi equal 0 for now. Sorry. So the probability to find a given value x phi of this homodyne measurement, it's simply given by the margin. It's given by the marginal of a quasi-probability distribution, which is called the Wigner function. So if we are in state psi, we can compute what's called the Wigner function of the state psi. I'll show you its definition in a second. And so you see, if we the probability that this homodyne measurement finds the outcome x phi is given by the marginal of the Wigner function taken for all the quadratures taken on all the complex numbers which have the right value of x phi. Okay, and the definition of the Wigner function. Wigner function of a quantum state psi taken at a complex number alpha. It's the average value of the parity operator. So here, parity operator, we can write it as exponential I pi a dagger a, taken on the displaced by minus alpha quantum state psi. Okay, so that's one definition of the Wigner function, which is very practical for in quantum circuits because we can measure it directly using precisely this measurement of the parity operator, which is something I'll show you later. Okay. All right. So this is how we compute the probability distribution of x phi. So that's for homodyne detection. Now let's move to heterodyne detection, which is another class of detectors. It's actually very similar to the previous one. So in quantum optics, it's a bit of a mess. But heterodyne detection essentially will measure. Okay, so in the frequency in the microwave domain, a heterodyne detector is something which works a bit the same. So we have a mixer again. Again, we have a microwave generator at frequency omega m and an ADC, and we measure. So it's exactly the same setup, except that now we will choose omega m to be far away from the frequencies of interest. So let me draw this. So if I plot here the frequency composition, the probability to find the mode f in a given frequency domain. So there will be let's say so this would be omega 0, or if it's the resonator of before, this would be the cavity frequency. We would have some line width, okay, which can be a kappa, let's say. And this frequency omega m, we will choose it to be away, so without any overlap with this wave function. So essentially there's no overlap. So this is very different from the homodyne case where omega m was right on top of omega naught, and in which case we measure a single quadrature of the signal. Here, because we will be away from omega naught, we will have access to both quadratures of the signal and not a single one. So we'll see what that implies. So the criterion is that omega m minus omega naught is much larger than kappa, than the extent of the support. Okay, so in In quantum optics, it's much more complicated actually. Maybe I will not draw it unless you, if you have questions, I can show you how it's done. It's essentially it's two setups like before. Okay, so this time we so how do we model this heterodyne detection? So this time the demodulation, so this weighing function demodulation is done at f of tau exponential I omega m tau. So that the demodulated quadrature, this x phi we had before, now it becomes a Hermitian, non-Hermitian operator. So it's the equivalent of this the observable we had before. It's non-Hermitian anymore. So it will be integral from minus infinity to infinity of f star of tau exponential minus I omega m tau x naught of tau d tau. We take the phase to be 0. And so this you see that this will be recast into we can express it as a function of the amplitude operators. So it will be recast as a f star of tau, integral of f star of tau a of tau d tau, plus integral from minus infinity to plus infinity of f star of tau exponential minus 2I omega m tau a dagger of tau d tau. Okay. So essentially we can say there's AF and another mode AF tilde star, and AF tilde star is f of tau exponential 2I omega m tau. Okay. So if I go back to the drawing above, this spectrum here, what are we talking about here? So we're saying that this new operator that we have access to will have essentially will be composed of the sum of two annihilation operators. Sorry, there's an annihilation and creation operator. This one has a dagger. So there will be two modes. One with a frequency f, which will have an overlap with the signal of interest, but another one which is a copy, a mirror copy along omega m. And so if you want, there is this new dark mode, f tilde, which also participates into this measurement. So the heterodyne measurement, it will have one benefit. It will have access to both quadratures of the signal, but at the expense of mixing the signal with some undesired new mode, f tilde, which at best will be in the vacuum state. But even in the vacuum state, because of the vacuum fluctuations, it will pollute a bit the signal of interest. Okay? So this is the heterodyne detection. Okay, so in this under the assumption of the homodyne detector, under this assumption that then the support, the frequency extent kappa is much smaller than the distance omega n minus omega naught, you see that there is no overlap between f tilde and f. Okay, so these modes are distinct. We can actually consider a hybrid measurement between homodyne and heterodyne, where there is some overlap, but I will not cover this case. Okay, so a few remarks. You see that this operator psi f is not Hermitian anymore, so it's not for say an observable. But what we are going to do in the experiment is that we will measure its Hermitian and anti-Hermitian part, essentially. Another point of interest is that psi f commutes with psi f dagger, which is pretty convenient. So even though it's not Hermitian, you see it still commutes with its Hermitian part, and and also it's two, so the Hermitian part, psi f plus psi f dagger over 2, and the anti-Hermitian part, so psi f minus psi f dagger over 2i, they also commute. So these are two observables. So maybe note that if we had a single annihilation operator of one mode here, this would not work. For a single mode, if we were to take the Hermitian and anti-Hermitian part of a single mode, they would not commute. And because of that, the Heisenberg uncertainty principle will tell you that it's impossible to have an infinite precision on both one quadrature and the other. So that's impossible for a single mode. But now that we have recast the problem and polluted our signal with this extra mode f tilde, now we have new variables, new quadratures that commute between each other, and so we can measure them. But you see that the pollution is there, and it will kick us back soon. Okay. So in order to determine the statistics, so again we can, as in the homodyne case, we can wonder what's the probability distribution to find two given real numbers here, or a complex number when we measure these two quadratures. And so to answer that, the simple way to see it is to compute the moments of these measurements. So let's do it. So we compute the moments. So the moments of these measurements. So let's say psi f. So an arbitrary moment is psi f to the power n times psi f dagger to the power m. Okay. So this would be the integral of the outcome psi f to the power n. Psi f star to the power n d psi f times the probability to find a given psi f. Okay, so the idea we are going to be interested in this probability, right? So one way to write this moment so is to replace. So I'm going to replace it with this expression. So maybe sorry to introduce a new variable, but this is a bit long to write, so I will call that B now. So BF, okay, BF dagger. Okay, so if you want to compute this, so this is equal to you see AF plus BF dagger to the power m, n times AF plus BF, so AF dagger plus BF to the power m, right? So now let's assume that we're in the best configuration, the less noisy configuration. We want to pollute our interesting signal with the least possible noise. So we're going to assume that the mode B is in vacuum, right? There's nothing, zero temperature zero temperature in this part of the spectrum. And so in this case, you see that we can develop this expression, but you see that each time that there will be a BF on the right, it will annihilate with the vacuum. So this term will vanish. And likewise, if there remains a BF dagger on the left, it will annihilate with the vacuum on the left as well. And so it will vanish. So in the end, the only remaining term in this big expansion is AF to the power n, AF dagger to the power m. So that's the only term that remains if BF is in the vacuum. All right. And so now there's an interesting. So now that we've done this, there's an interesting point, which is to say that you see that it's an anti-normally ordered. So it's an anti-normally ordered expression for AF. And actually, that's the signature of the moments of the UZIMI Q function. So moments of the UZIMI Q function. So what we have shown here in a few lines is that the probability distribution that we are looking for, the probability distribution that we find a measurement outcome for psi f, let's say x plus iy, that we find a given value x and y, is directly given by the Q function, this UZIMI Q function, of the quantum state psi of x plus iy. So maybe I can remind you what's the UZIMI Q function, right? So the UZIMI Q function of a quantum state psi of alpha is 1 over pi times the square of the scalar product alpha times psi by psi. Interestingly, it's also another very nice expression is that it's the convolution of the Wigner function by the Wigner function of the vacuum. So if you want, the Q function can be seen as a blurred version of the Wigner function. Okay. All right. So these are the two probability distributions for homodyne and heterodyne detection, and so maybe a final word on heterodyne detection. For the ideal heterodyne detector, the measurement operator, the Krauss operator that describes, or the P of M, it will be a projector here, that describes this measurement is 1 over square root of pi alpha alpha. Okay. So you see this, so these coherent states alpha, they define the measurement operators of the heterodyne detection. Okay. All right. So maybe now let's address the final. So Pierre mentioned a theorem saying that there are only for Markov dynamics there are only Wiener processes and Poisson processes. I didn't know that, but so we will. So we covered the two kinds of Wiener processes we can make, and now we'll do the jump, the Poisson processes, right? So photodetectors. All right. So how do we model photodetectors? There's a continuous version. The continuous version is that the observable is simply a dagger of t, a of t. All right, so that's an observable. The eigenstates and eigenvalues of this operator are such that a dagger of t, a of t. So they're of the shape a dagger of t prime of the vacuum. You see, if you create indeed a single photon at a time t prime, we now know how that works, right? So this will be a delta t minus t prime, a dagger of t prime vacuum. So these are the eigenstates of the photodetector. So this is the kind of states that are detected, right? And these are the clicks that Pierre mentioned, and I mean, and several others, and Huard. But so these model the clicks, right? And these are the eigenstates. So we can do all right. So how does that look in practice? So let me show you a couple of experiments that try to implement this with superconducting circuits, which is not natural because, as I mentioned, the very tiny energy of microphotons compared to the gaps of any semiconductors forbids us to use semiconductors as detectors. So we have to be smart, and so maybe to give you an idea of this field, right? So here are several proposals. So let me try to get my pointer. Okay, so here are several proposals for microwave photodetector. So the first experimental work was done in Madison in 2011 and used a Josephson junction as a detector. So the junction essentially the junction excitation, and hence voltage measurement is triggered by a single photon. There have been a few other works exploiting the dispersive Hamiltonian of a transmon coupled to a cavity, which changes essentially so when a photon is impinges on the cavity, the phase of the superposition of the transmon changes. But I'd like to discuss this work by my friends and colleagues in Paris. So this is a very elegant photodetector, and this will allow us to discuss one example of reservoir engineering for a quantum application. So indeed, this experiment is based on reservoir engineering. So it's made of a few elements. So there are two resonators. One is a buffer mode. It will be at the frequency of the photons we want to detect. And another one is called a waste mode. The waste mode is strongly coupled to the outside world, including a measurement setup. And here there's a qubit that couples the two. So the qubit is dispersively coupled to each of them, but also interestingly, because of the nonlinearity of the transmon, this qubit is able to induce this four-wave mixing interaction term. So it's an interesting term. You see, there's a term that so the term is like that, right? So there will be the annihilation of a buffer photon. So when the photon comes in, you see the photon arrives. It will because of this term, it can be annihilated, and it can in turn excite the transmon in the excited state, and the waste mode, the green mode, in the excited state. Okay, so now this incoming photon will be converted into a qubit excitation and a waste excitation. So if we stick to just that without reservoir engineering, we will have the issue that the reverse process is possible. Right? The Hamiltonian is not non-Hermitian like yours. So this process is possible if we do nothing. And so this excitation of waste mode and qubit will be converted back into a photon here. And so we cannot use that to detect. So if we want to measure the qubit, it's too late. You know, the photon came out. So what they engineered, which is very beautiful, is that they suppress this extra term in the Hamiltonian. And the way they do it, the way they effectively render the Hamiltonian non-Hermitian, is that the waste mode is so strongly coupled to the outside world that as soon as the incoming photon has been converted into a qubit excitation and a waste excitation, the waste mode decays. So the waste mode will lose its excitation, and hence the system is stuck because this. Okay, the waste is empty, but the buffer is empty, so this cannot be activated. And here the waste is empty, so we cannot annihilate the waste anymore. So it's so you see that because of that, they managed to convert effectively an incoming photon in the buffer mode into a qubit excitation, and this is latching, right? The qubit will stay excited for as long as its lifetime permits. And so then at some later time, we can decide to measure the qubit state and check whether or not the qubit is excited, which would be a click. So this is a really beautiful setup. So it's been so this was the first of this series of work in 2020. Now they've managed to make it frequency tunable, and the Dhar count rate is much lower than everything else on the market. And with this, they've been able to see the fluorescence to sense a single electron and even a single nuclear spin. And they're now using it for action research. So, but you see, this could be used. So this I would say is our best shot at a photo detector in superconducting circuits. So of course, it's not. There's some time scale. It's so again, it will be discrete, right? Because you don't know when the photon arrives during this one cycle of this operation. But again, the cycle duration can be tuned, right? So this is very nice. So another experiment I'd like to discuss is one where we can photo count. So not only photo detect but photo count. So we can count the number of photons in a propagating mode. So this there's been a proposal in Sherbrooke, but I'm going to show you our experiment, which is not based on the proposal. So this time we again have to know the shape of the mode we want to photo count, and it works based on a circuit which is called the Josephson ring modulator. The Josephson ring modulator this time is a three-wave mixer, so it's a three-wave mixing term. Then there are three modes, and they're coupled through this mixer. But what that means is that we can so if we pump this circuit at the difference between the frequencies of omega m and omega b, we effectively activate a conversion. For one photon of the buffer is converted into one photon of the memory and back. So this is noiseless frequency conversion. We can also activate a two-mode squeezing Hamiltonian if we pump at the sum of frequencies, which we use to demonstrate a quantum advantage in radar, but this is not the topic of the talk. And so okay, let me schematize the setup like this. So there will be an incoming wave packet arriving here, and we want to know how many photons there are inside. So it will be so the buffer will be able to will be more or less matched to this incoming mode. So when the photon arrives, the buffer gets populated. But then we turn on the pump so that we convert everything that's coming into the memory. And if we choose properly the shape of the pump amplitude, we can catch optimally this incoming mode into this long-lived cavity. So second step is to use the qubit as a counter. So we can count the number of photons in the memory in the way I'll show you. So we encode the qubit, the number of photons into the qubit state, and then read it out. And finally, we can reset by again converting this state back into the buffer and letting it go away with the quantum back action have been exerted. So ideally, a photon number is prepared. So this is the circuit that we've designed. So in orange, we have the buffer. In purple, we have this memory mode. The qubit is in green, and the readout resonator of the qubit is here in gray. So yeah, to give you numbers, 10 gigahertz for the buffer, much lower for the IQ memory. Okay. All right. So maybe I can show you how we can adapt to the shape of the signals that are coming in. So let's say we don't know the shape of the incoming signal, but so let's say Alice prepares the shape of the incoming signal, and Alice prepares either this one, that one, or that one, and we want to know which one she prepared. So one thing that we can do quite simply is instead of having a long pump tone, what we do is we have a short pump converting pump pulse, so that we convert the photons only within a given time window. And if we change this time window and photo count at each of these possible time windows, we can reproduce the incoming wave packets that Alice sent, and you see that there is some finite filtering. So the sharp features of the ears of Batman here have been a bit distorted, but still you see that it works quite well. Okay. So how do we optimize the pump the amplitude of the pump we need to send to optimally catch an incoming wave packet. So this is a flat output problem. So we want that during the incoming during this incoming pulse, we want that no reflection occurs. So the criterion is B out equal to 0, and the question is, what do we send? What is the pump we need to send, right? So we can solve this. So we write the Langevin equations. So these are the input-output equations. In the language of what I described in the talk before, B in would be the propagating mode towards the downward propagating mode here, and B would be the intra-cavity annihilation operator. P in would be again the amplitude of the incoming pump mode. So these we can write these Langevin equations here, the input-output relation, which is similar to in what I described earlier, to saying that the voltage at a position is the sum of the leftward and rightward propagating voltages. Okay, so we can. I'm sorry? M is the memory mode. Yes, absolutely. M is the memory mode. Thank you. So with this, you see, so if we send, if B in is this Laurentian shape, solving this tells us that B in should be matched according to this purple line. And if we are very nice with the experimentalist and design a B in which is exactly of that shape, so an exponential rising and then quickly decreasing, then the optimal pump pulse is a square shape. Okay, so effectively we were able to catch 92% of the incoming power. Okay, so how do we count with the qubit now? So there are several ways to do it. So this one is kind of optimal in some sense. So so if we write the number of photons if we write the binary decomposition of the number of photons, okay, so this is the least significant bit, second least significant bit, etc. We can write this, and so the game now is to encode into the qubit state each of these bits and decode the number of photons one bit by one bit. So this is the algorithm that we're going to use. It's an algorithm that was actually proposed by Serge Haroche and Jean-Michel Raymond in 1992 in the context of cavity QED. And so the way we do it is the following. So we just use the dispersive Hamiltonian again that we discussed yesterday. So to probe the least significant bit U1. So you see this bit tells us the parity of the quantum state, right? So we just have to measure the parity of the number of photons. And the way to do it is to first do a pi/2 pulse, unconditional on the cavity state. So we do a fast pi/2 pulse on the qubit. Now it's on the equator. And then we wait for a time pi/chi. Waiting for a time pi/chi, due to the dispersive Hamiltonian, you can see that the block vector will rotate an integer amount of turns if the parity is even, and a half integer if it's odd. And then we map these two quantum states back again with a pi/2 pulse and measure. And you see that we now have measured the parity of the qubit. So that's for the least significant bit. If we want to measure the second least significant bit, so there are two ways to do it. The way we did was to use feedback. So we do a pi/2 pulse again, and then we wait for a time which is now shorter. It's 2 pi/2 to the power k chi. K is the number, the index of the bit, and we do a final rotation, which is conditioned. The axis of rotation is conditioned on what we measured earlier. So on the other least significant bits. So if we do that, we can encode bit by bit the decomposition of the number of photons. So here you can see the results of the experiment in green, which predict the probability to have 0 photon, 1 photon, 2 photons, 3 photons, as a function of the the number of average photons we put in the cavity with the coherent state. So yes, and so this is a reproduction of what the quantum state of the cavity is after the measurement. So ideally, it would be the Fock state of 0, 1, 2, 3. But owing to imperfections in the measurement, you see that the state 2 is somewhat mixed with 1, and state 3 does not look like a Fock state at all. If we compute from there the fidelities of the detection, so the fidelity of detection, doing something completely random would be 25%. So we are between, let's say, 56% for the worst case, Fock state 3, and 99% for Fock state 0. Okay. So, yes?
So you're using the qubits to measure repeatedly one pattern? Or are you repeating successive experiments?
Here you mean? So here each point here is one experiment that we repeat many times for a given value of alpha squared. So you see that ideally you would see the Poisson distribution of coherent states. So each point would correspond to the 4 first weights of the Poisson statistics, so these would be the dashed lines. Yes.
Per catch.
Yeah, absolutely. Yeah. Per catch, we measure the qubit once for the first bit, reset, do a second one, third one. Yeah. So we reset the qubit, but not the cavity, right? We use the same qubit multiple times. Okay. All right. How am I doing on time? Okay. So yes. So I wanted to discuss amplifiers, but maybe I'll report the discussion on amplifiers to Friday, because I really want to, given the talks of this morning, I think it's a good time to show quantum trajectories again. So okay, let's dive in this part 3. So here I would like to show you various experiments that probed quantum trajectories with these systems. So the first 3 parts will concern the quantum trajectories of a single qubit. Then we'll discuss the quantum trajectories of 2 qubits, so with entanglement, and the final part will discuss the tracking of the photon number in a cavity, owing to a qubit. Okay. So the first part we already covered yesterday. So this is the continuous dispersive measurement of a qubit state. So you see, if we send a drive at the cavity frequency, I remind you that if we measure what's coming out, we will get. So this is described by a measurement of a jump operator, which is in sigma z. And the rate of measurement is here called gamma d, and we can tune this rate by changing the amplitude of the incoming drive. So in the language of quantum trajectories that we saw this morning, so the measurement record that's going to be recorded by the detector. So here I focus on homodyne measurement for this one. So it's a single measurement record because it's homodyne. And here we will record something which on average is given by sigma z times the square root of the measurement rate. And here there's an extra factor, which is the efficiency of the measurement. The efficiency of the measurement tells you what's the frame. Let's say it's by how much your signal-to-noise ratio is preserved from the qubits, let's say the output of this cavity to the detection setup. Or in a phrase in a different way, it's the fraction of the noise you measure with the analog to digital converter, is a fraction of the noise that you measure here that comes from the amplified vacuum fluctuation of the noise at the beginning. And why is there a 3? Because this is extracted from a talk where there are 2 other processes. But you will see this part later. Yeah, I forgot to remove this one. All right. So you have this average outcome, and then the Wiener process that characterizes that's the discovery, right? The innovation. So the noise. And so we can do a stochastic master equation using this record, which is exactly so now there's a single master equation, stochastic master equation. So the stochastic master equation, and solve this, right? And we get the results I mentioned already yesterday. So this kind of quantum trajectories. Okay. So this morning, Keiter mentioned the case of the fluorescence of a qubit. I'm going to discuss that as well, but maybe extending a bit more and discussing the heterodyne case. Okay, so to go back to this very simple gedanken experiment. So let's say we prepare a 2-level system in either the excited state or the 0 + 1 over square root of 2 state, and we let it decay. So if we let it decay, on average, sigma z will simply decay with a time scale t1, the lifetime of the qubit. And if we plot sigma x, so sigma x, if we prepare the qubit in this superposed state, it will decay at a rate t2. But if we start from the excited state, the trajectory, the average trajectory will actually go directly down the z-axis, so there will be no coherence build up. It will stay at 0. But if we instead, if we don't let this 2-level system release an excitation in the environment, and instead look at what's been released, so we can do this conceptual experiment that Keiter already showed this morning. So we surround ideally this atom, let's say, with many photodetectors, so that no hole like this one is left. So we will record events like this, so a click. And now if we plot the quantum trajectory of this system condition on the measurement record here, if we prepare state 1, as long as we don't see a click, well, it stays in 1. If instead we prepare 0 + 1 over square root of 2, you see that the no jump trajectory, so the fact that we condition and the fact that we didn't see a jump diminishes the probability of excitation. And this is to say that if it was excited, well, we would have some probability to see a jump. So if a click. So if we don't see a click, it means that it's more and more biased towards not being excited. And when there's a jump, well, it jumps to the ground state, and that's it. Okay, so it would be great to see this kind of trajectories, but as I already mentioned by Keiter, this is not physically realizable. But what we can do instead is try to channel this excitation, the decay, the spontaneous emission of the qubit. We can try to channel it out in a microwave cable and measure it with a homodyne or heterodyne detection. So fluorescence measurement of quantum systems has been done in many platforms, including superconducting systems back in 2010. What we're going to consider in this experiment is again a transparent qubit coupled to a 3D cavity. It will be coupled now to a transmission line, and we couple it sufficiently well enough so that the relaxation of the qubit is dominantly going through this output microwave cable. And then what we're going to do is amplify with a phase-preserving amplifier. So we amplify both quadratures and perform a heterodyne detection. So this time, for this one, we will have two measurement records corresponding to the Hermitian and anti-Hermitian part of this outgoing field. So the mean signal that's coming out is proportional to the decay, to the lowering operator of the qubit. lowering operator of the qubit, you know, it's the operator that goes from the excited to the ground state. And so indeed, if we look at average values only, the real part of the sigma minus operator is sigma x. Maybe I should go back for this. So the real part of the Hermitian part is sigma x, and the anti-Hermitian part is sigma y. So on average, so these average terms in the two measurement records we get are proportional to sigma x and sigma y. And again, we have an efficiency here, which corresponds to how well we amplify this and measure these quantum signals. Okay, so now we have these two measurement outcomes, and you start to see why there's a 1 and a 2 and a 3 now. So the average outcomes are here, and we have two Wiener processes, each corresponding to one of the two quadratures that are measured. Okay, so again, we can do a stochastic master equation out of these two measurement records and compute the density matrix as a function of time of these qubits. So let me flash the stochastic master equation here. So we start from the Lindblad master equation. We have three possible measurement operators in everything I'm going to discuss. So for the present part, we have two measurement operators corresponding to the two quadratures. One is sigma minus and the other is I sigma minus. And when we measure the dispersive, when we measure sigma z, this would be the measurement operator instead. So if we look away, if we record these measurements but throw away the hard drive, we will be stuck with this master equation alone. But if now we find the hard drive back in the trash and get the information we were missing on what's been recorded, we can extract from the measurement records, we can extract this Wiener processes value, and we can put it in with this innovation term. We can put it back in this stochastic master equation. This is how we solve here the stochastic master equation. To give you a picture of what's going on, so this is one experiment where we measure we measure the two quadrature as a function of time when the qubits start in the excited state, and solving the stochastic master equation shows a trajectory which you see looks like this. So it kind of ends up close to the ground state here. If we plot 5 different trajectories, this is so each color corresponds to one experiment, and you see 5 possible trajectories that each go from the excited state to the more or less the ground state. Okay. All right. So then there's this interesting point of being able to show that these quantum trajectories, the solution of the stochastic master equation is predictive. So what does it predict? Well, so this has been a bit discussed yesterday as well, but I'm going to again discuss it because it's very important. So this has any interest if it predicts something that can be experimentally measured. And what can be experimentally measured is so what we would like to do ideally is measure many of these measurement records. Ideally, find 1,000 experiments where we get exactly the same measurement records, and end up by doing a quantum state tomography of the qubits after these 1,000 records, and compare the prediction of the stochastic master equation, which I call X traj, Y traj, Z traj, to the result of the quantum state tomography. But of course, we cannot find 1,000 experiments with the same noisy measurement records. So what we can do instead is sort the predictions, so sort these quantum trajectories, and pack them in such a way that we will make an ensemble of experiments that are predicted by the stochastic master equation to end up within a vicinity of X traj, Y traj, Z traj. And for this ensemble, we will compute the average value of x, y, and z that we have measured by projective measurements at the end of the experiment. Okay, and so if the quantum master equation is good at predicting anything, it should be able to. We should have a good match between this point in the Bloch sphere, in the Bloch ball, and the outcome of the tomography. So this is what we did. We compared we compared the trajectories after 4 microseconds of integration. We compared when the qubit starts in the ground plus excited state or the excited state. And here you have so each dot corresponds to this packing I mentioned, and compares x, y, y tri, z tri, each in color, with the result of the tomography. And as you can see, it indeed sits on a straight line. There is actually one knob in this endeavor, which is the efficiency, which we don't know very precisely. It turns out that this procedure is maybe the best one to determine the quantum efficiency eta. And here we got 24% to get a good match. If we were to deviate from 24%, if we do 28%, this curve is not a line anymore. It would do some parabola. Okay. So then we had fun, right? So we wanted to show statistics of these quantum trajectories, and here I'm going to show you a movie where we start in either the equator on the equator of the Bloch sphere or on the north pole of the Bloch sphere, so excited state, and I'm going to show you a movie of the distribution of the Bloch vectors in color as a function of time. Okay. So we do it for 1 million of experiments. We compute all the solutions to the stochastic master equation and plot the distributions of the Bloch vectors. So you see at short times we are really close to the initial point, right? So it starts to diffuse a bit. So instead of a single point, we start to have some kind of Gaussian spread. Same thing for E. But when we plotted this, we had the surprise to see these dynamics. So you see it kind of looks like a shrinking ellipsoid, and indeed we were really puzzled by this. So we looked and discussed a lot with Pierre Rouchon and Alain Sarlet about this, and you see these dynamics indeed looks like it starts to unroll over this ellipsoid, and indeed what Pierre and Alain discovered is that there is some very rigorous relation that tells us that the Bloch vector, it actually lives on an ellipsoid with some parameter that describes the shrinking of the ellipsoid, which is perfectly deterministic and depends on the quantum efficiency. And in this paper, they generalized this kind of constraint to many possible quantum systems. And this kind of dynamics, by the way, we have a paper with Andrew Jordan and Arya Shantasri on using the path integral formalism to characterize the statistics of these trajectories. So something that also that I find very interesting and that's related to a paper by Klaus in 2014 is that it's you see there are trajectories where the energy expectation can increase. So this is particularly disturbing at first, right? You start from here an average energy which is a half of a photon, and you measure the spontaneous emission of this system, and so you expect the energy would go down, but in fact quantum mechanics tells you that no, it does not necessarily, and there are some trajectories where the energy goes up. So it's been studied very carefully in this paper, and so this is really one more proof that conditional probabilities are really not made for human beings. This is very so that's really linked to the information update of this these measurement outcomes. But despite the fact that this measurement comes from the de-excitation of a qubit, the spontaneous emission, it's possible to have energy increasing on average. Okay, maybe how much time do I have? So yeah, so maybe I will conclude with the measurement of both. So you see, we now have two baths, one for relaxation, one for dephasing. So and I showed you two measurement apparatus, one for sigma z, one for the fluorescence, so sigma minus, let's say. But these two seem like incompatible measurements, right? One wants to measure sigma z, the other one measures kind of a hybrid of sigma x and sigma y. So somehow it's as if we were measuring with these three measurement records, we are measuring on average sigma x, sigma z, and sigma y. And so the question is how do these measurements interfere, you know, and who's right, who's wrong? So this kind of interesting questions. So this is the measurement setup I'm going to describe now. So we have again this qubit in cavity. We drive the qubits both at the cavity frequency to record, to extract this measurement record on sigma z. And we drive it also on resonance in order to create Rabi oscillations. And we record the spontaneous or simulated emission of the qubit by these two other measurement records. So we have these three records, okay, so now we know how that works, right? So we can apply the stochastic master equation here in its full extent. So we have three Lindblad terms, three corresponding innovation terms, three Wiener processes, and we can compute these trajectories. So first, what's nice about this system is that if we do a direct averaging of the measurement records without any further processing, we get, you see, the three coordinates of the block vector. So this is an example where we don't need to do gate operations, unitaries on the qubit, and followed by measurements to do the tomography. We can do a full quantum state tomography by just turning on these measurement channels and averaging the output. And this is what we get. For instance, if we here I show you two Rabi oscillations. One when the measurement of the z of sigma z is weak compared to the Rabi frequency, so we still see Rabi oscillations. And here one where the measurement rate of sigma z is strong. And so owing to Zeno effect, we overdamp these Rabi oscillations. But you see that each of these points has been obtained by direct reaveraging of the three measurement records. All right, so how does it look, right? So so here I'm bothered by the fact that the title is missing, and I can't remember exactly. Yes. So is it possible to move this? Maybe if I press OK. Right. Sorry, I should have done that before. All right, so one quantum trajectory. So let's look at one possible quantum trajectory. So on the right, you will see a movie of one experiment. So you will see three measurement records. You know, the color indicates which is which. And on the left is a solution of the stochastic master equation. So this is a single experiment. You see, we have very noisy measurement records because, as Pierre mentioned this morning, the Wiener processes are actually much larger than the signal itself. But on the left, you know, the stochastic master equation is brave enough to make something decent out of it. And so we see some Rabi oscillation at the level of single trajectory. So we can do two experiments. And so here you see two very noisy measurement records corresponding each to a different quantum trajectory in time. Again, you see oscillations, right? So this, indeed, these are Rabi oscillations. You see here the red one, it's stuck near the North Pole, and this is due to Zeno dynamics, so Zeno effect. The measurement of sigma z somehow stucks the trajectory on the North Pole, but sometimes it can escape. So we are going to, so we also validate, we do the same, right? So we check that the the prediction of the stochastic master equation matches the tomography measurement, and it does. And what I'd like to show you now is again statistics, right? So you'll see a movie of the statistics of the block vector as a function of time. And but now it's getting interesting, right? Because we have these two detectors. So what we're going to do is consider one detector at a time. So let's say there are three players at the casino, right? They want to use a qubit to make bets and win money or not. And one player has access to sigma z, the other one to sigma minus, and the casino owner has access to both, right? So who's going to win? So this one is the player with sigma z only, and you see the statistics of the trajectories looks like this. So here I represented a single trajectory again, so that you see what one trajectory looks like. You see that there's a big concentration of weight at the poles, which is due to the Zeno effect again. So here the measurement rate of sigma z is the largest scale in the problem. It's about 10 times larger than the Rabi frequency, and which is about 10 times larger than the lifetime of the qubit. And so you see this is why Zeno works well and blocks the dynamics at the North Pole. If we were to look at the average trajectory, the solution of the master equation alone, this would be this overdamped oscillation here, very boring one, right? But if we look at the trajectories, it's beautiful. And you please note that if we look at the other two quadrants, so if we look at XY or YZ, you know it's a single line, and that's because there's no back action or unitary dynamics that moves y sigma y from 0. Sigma y stays 0 for the whole time. Okay, but now if we are the other player at the casino and use sigma minus only, so this player is actually a bit the unlucky one, because the efficiency of this record was 14%. So it has access to less information. But you see that the dynamics is very different. So this time the prediction that this person will make will be quite poor. The statistics is centered on the block sphere. But what's new is that maybe this person could say, okay, let's bet on sigma y, and then he would win, right? Because you know sigma y now has some extent. And indeed, it's possible to make a better informed guess about the value of sigma y with these measurement records than with the measurement records of the player who had sigma z. But of course, the casino owner has both, and so if we take into account both, then you see the casino owner will be able to make bets maybe that with some angle in XY, and they will be the one to win. Okay, so here's a summary of these three competing statistics, right? And you see that indeed there are very different measurement back actions for the three of them, and again we see the Zeno blockade as a concentration. Yes, the colors are indeed, so this is a snapshot at a given time, and the color indicates the density of trajectories that are at that point at a given time. Yes. Okay, and so this is this measurement of sigma minus sigma z. I'd like to point that there has been 2 years before a beautiful paper by the Berkeley group that measured both sigma x and sigma y. So not using so it's not measuring really sigma minus as we did. It's measuring really sigma x and sigma y continuously using sidebands of the cavity. And here what they measure. So if you measure sigma x and sigma y and look at the statistics of the trajectories on the equator, you see that there's a diffusion owing to the kicks of the back action of the measurement. there's a diffusion of the trajectories around all the equator. Whereas if you measure sigma, so what is it? It's a sigma y and something which is a quadrature which is a bit tilted, so a hybrid between x and y, but pretty more y-like. Well, then the back action makes the statistics stay around the plus and y states. Okay, so it's actually possible to change the parameters, right? The system is very tunable. So here we show a weak measurement of sigma z and a slow rotation. So this is the opposite configuration where you see gamma, the measurement rate of sigma z is now comparable, is equal to the decay rate of the qubit, so to the measurement rate of the fluorescence operator. And now the fluorescence, if we look at the fluorescence alone in this configuration, you see that the trajectory is very different again. And this time it has much more information than in the xeno-blockaded case. Okay, and here I can show both. This is so you see there are very nice properties of these statistics, which you can write a Fokker-Planck equation actually to describe what they are. And this is the statistics of in this other configuration. So if you want to look at all possible configurations, I invite you to go to our website, and there's some app that you can play with and look at the experiments we did on all the various parameters, of Rabi frequency and measurement strength. Okay, I'll stop here for today. Thanks.
For the nice talk. So if there is any question, please ask Benjamin. Yes.
Behind you.
So thanks. Is it the case that the effective measurement rate, the gamma you associate with it, with the spontaneous emission case, that depends on where the state is in the Bloch sphere, that there's more back action when it's near the excited state? And I saw in the last graph you show the sort of measurement rate arrow is shifting in time. So does the effective measurement strength,
yes,
spontaneous emission change in time?
Yes, so the way to maybe represent this is to plot the action of this. So in the stochastic master equation, there is this M operator, right? That characterizes the back action. So for instance, for the fluorescence part, if I plot a field of a field of back action of the fluorescence, it will be something that gets lower and lower as you end up in close to the ground state. So it's true that the strength of the back action will depend on the point on the Bloch sphere. So now to define the measurement rate, this is so there are indeed many possible definitions. The one that I use is one where you start from the most entropic state, the center of the Bloch sphere, and you see on average what's the reduction in the entropy you won by doing the measurement step. So if you do a measurement, there will be you will win a bit of information, so you will decrease the entropy, and the average entropy decrease is the measurement rate. So there might be a log 2 depending on definition, So but this is true here, and as you say, it indeed depends on the point. Yeah.
Is there any other question?
Sorry, I just want to go back to the point number 2, which is this measurement apparatus. And you had shown us this model which basically involved this these two harmonic modes with very strong damping.
Yes.
So this Benjamin, this reminds me a lot of sideband cooling. No, it was in the slides already. Sorry.
Oh, I'm sorry. Yeah. I was happy that this worked, but all right. So let's see. So you say 3.2, right?
No, I think it's towards the end of 2.
At the end of 2, okay.
Or maybe, you know, the one where you had very strong damping into the cavity. It was a detector design slide.
Is it this one you're referring to, or maybe the Zeno effect?
Yeah.
Ah, yes.
Yeah, that one.
I'm sorry. Thank you. This one, right?
Yeah. And so what I was wondering was like the kind of trick which was in a Hamiltonian in a couple of steps before. The trick seemed to be that you basically have like a very strong damping in one of the cavities so that the Hamiltonian effectively acts as a detector. The Hamiltonian action acts as a detector, so it doesn't repump the system.
Yes,
right?
yes.
So this reminds me a lot of sideband cooling, right? This is exactly the same trick as sideband cooling, exactly this one. And so I was wondering, you know, people have tried to, you know, this is steady state. If I was to think of this as sideband cooling, this is steady state, but you could also do transient cooling. Mm-hmm. And we've done stuff like this where we've shown that the transient cooling regimes can be like 4 orders of magnitude better than the steady state cooling. And so I wonder, Benjamin, I just ask you this question, which is in terms of detector design, would it actually be an interesting thing to apply optimal control to the pump in the cavity to try and make sure that you shunt the photons the moment they interact with the cavity, that they shunt it to the right?
So yeah, it's a very interesting point. I think the one thing to consider here is that the dynamics of this, so the cycle of this detector is that there's a detection step. So this would be time, right? So there's a detection step during which the pump is turned on in their case. So in their case, it's flat, right? And then there is another sequence. So that's a time detection, and there is another sequence which is the measurement of the qubits. So here they need some time to extract information from the qubit. So this time is finite, right? So I would say if you want to do optimal control on the pump, that's a good strategy. But I would expect that this works only on a very finite time window. Otherwise, right?
I see. I'll just talk to you in private because I don't understand this point. Maybe
okay,
it needs more explanation.
Maybe basically, I think you want the duty cycle, you want the detection time to be much longer than the measurement time of the qubit.
Oh, I see. Yeah. Sure.
Otherwise, your system basically lose all its time measuring the qubit, which lowers the efficiency. But maybe there's a...
Yeah, let's just talk.
Yes.
Thank you. So in the case of the dispersive measurement of sigma z in the superconductor qubit, so have you seen absorptions? So it's possible to observe like absorptions like of the external environment?
So
or is this so? It is so cold that you don't see it ever.
So you're asking whether the measurement is actually QND or whether during the measurement there can be
yeah. So since you are like looking at sigma z, if you see like some absorption of
yeah. So indeed. So what I didn't talk about that at all, but indeed this is a very important topic that for quantum computing, for instance. So we may think that increasing the measurement rate is as easy as turning on as increasing the amplitude of the drive at the cavity frequency. But actually, the reason why there's a limit is that if you increase it too much, we start to see excitations or the excitation of the qubit state owing to the coupling to the population of the memory. So if you want, this comes from the fact that the dispersive Hamiltonian I wrote was under some assumption, an approximation, right, which started from a transverse Hamiltonian, let's say James Cummings. And this comes back to here to bother us. So indeed, there is so the measurement is approximatively QND. So it's in the sense that it's approximatively the dispersive Hamiltonian. There are other issues that may arise due to the dynamics with a large number of photons. But yes, but apart from that, there's no impact. There are some works where that implement an actual dispersive Hamiltonian from the start with a more complex circuit, and these ones are much less affected by these non-QND effects.
Thanks. Thanks for the great talk and those wonderful results, which I hadn't seen before from your 2018 paper. But I wanted to ask a question about where you catch the mode and do the Roche style.
Yep.
So you said you had a 92%. You probably answered this, but I wasn't paying attention. You had a 92% efficiency for catching the mode. But then, what's then like the quality loss in the actual readout of the number of photons using the atom?
The reason for the loss of efficiency. You mean the reason for the lack of fidelity?
How do you quantify the imperfection in then doing the readout? Could you think of that? To what extent is that equivalent to just having more loss, or can you not think of it in that way? And quantitatively, how big is it?
Yeah. So currently in this experiment, we were the errors were limited by the qubit and memory lifetime essentially. So the problem did not come from indeed from the inefficiency of the catch, which was very low. Okay. But in this case, if I remember well, the cavity, the memory was 4 microseconds long. You know, the lifetime. So it's a nice name to tell that it's a memory, but.
Okay, so you're not quoting an overall efficiency because it's going to be a lot less than.
Yeah. I mean, the issue is that if you want to discriminate more than 2 scenarios, so here we do photo counting up to from 0 to 3. There's not a single number we can give anymore. Yeah. And so this is why I show this table, right? Which is the error for each the assignment error of this detector, depending on the input number of photons. So this is okay. If you want to look at the diagonal and give an average value, this would provide maybe one number.
But this is really single shot.
So ideally, yes. So this comes from So this comes from simulations of. The experiment is this one. It uses coherent states. We do a simulation and see that we reproduce more or less the experiment with a solid black line, and from the simulation we infer what would have happened if we had sent a Fock state.
Right,
so,
yeah. Thank you.
Yes.
So just looking at that table, is there a particular reason that you mistake by 2? I mean, the 2 photon state is mistaken with the 0 photon state as maximum and 3 with 1.
Yes. So the reason why is so this really fully depends on the encoding of the bit string. So if we were to encode the Fock state 3 in the state 0, 0 of the qubit, then we will be much less sensitive to the qubit lifetime. And this would be a bit reversed, right? So these weights are due to the fact that indeed the Fock state 1 and 2 correspond to having either 0 first and then 1, or 1 first and then 0. And so they're both affected by the possible decay of the qubit. Yes, that's right.
May I ask you a question also? I'm not sure if I understand well how you optimize the power of the input.
Yes, it's a flat output problem. So we write these Langevin equations, and we solve these equations under this constraint that we want B out to be equal to 0. And and knowing B in, you see that so B in is given, right? It's the orange shape. Then indeed you can replace. So if B out is 0, you can replace, let's say, the B in by a B here, and you end up solving the equation for P in, which.
And the next lecture is about feedback. So
the next yes. So I will. Well, yes, not only, but yes.
Okay, thank you very much. So if there is no more question, can maybe.
Okay.